Q learning algorithm is an algorithm which is value-based learning algorithm in reinforcement learning. We will here see about Q learning algorithm and a few of its details. We will first go ahead and see what is Q learning algorithm, and then we would see the mathematics behind Q learning. Thereafter, we see the implementation of this Q learning algorithm using Python. To start off, let's see what do you mean by a Q learning algorithm. For this, I consider the case of a robot. Let's say that a robot has to cross a maze and reach the endpoint. There are mines, and the robot can only move one tile at a time. If the robot steps onto a mine, the robot is dead. The robot has to reach the endpoint in the shortest time possible. Here, we will consider the scoring or the reward system as under. The robot loses 1 point at each step. This is done so that the robot takes the shortest path and reaches the goal as fast as possible. If the robot steps on a mine, the point loss is 100 and the game ends. If the robot gets power as shown by the lightning symbol, it gains 1 point. And if the robot reaches the end goal, the robot gets 100 points. Now, the most obvious question is, how do we train a robot to reach the end goal with the shortest path without stepping on a mine? Kindly see the figure as under, which is shown on the slide. How do we solve this? So, we introduce the Q table. Q table is just a fancy name for a simple lookup table where we calculate the maximum unexpected future rewards for action at each state. Basically, this table will guide us to the best action at each state. Kindly look at the slide, the figure which is shown in the slide. Here, there will be 4 number of actions at each non-edge tile. When a robot is at a state, it can either move up or down or right or left. So, let's model this environment in a Q table. In the Q table, the columns are actions and the rows are the states. The same is as shown in the slide herein. Each Q table score will be the maximum expected future reward that the robot will get if it takes that action at that state. This is an iterative process as we need to improve the Q table at each iteration. But the questions that arise are: first, how do we calculate the value of the Q table? Second, are the values available or predefined? In order to learn each value of the Q table, we use the Q learning algorithm. We will now see the mathematics behind the Q learning algorithm. The Q function uses the Bellman equation and takes two inputs, that is the state denoted by S and action denoted by A, and is as shown in the slide in the form of a mathematical equation. Using the above function, we get the value of Q for the cells in the table. When we start, all the values in the Q table are zeros. There is an iterative process of updating the values. As we start to explore the environment, the Q function gives us better and better approximations by continuously updating the Q values in the table. Now, let's understand how this updating takes place. There are various steps for this. The first step or step number 1 is to initialize the queue table. We will first build a queue table. There are n columns where n is equal to the number of actions. There are m rows where m equal to number of states. We will initialize the values at 0 as shown in the slide herein. In our robot example, we have 4 actions, that is A equal to 4, and 5 states, that is S equal to 5. So we will build a table with 4 columns and 5 rows. Step number 2 and 3 is to choose and perform an action. This combination of steps is done for an undefined amount of time. This means that this step runs until the time we stop the training or the training loop stops as defined in the code. We will choose an action A in state S based on the queue table. But as mentioned earlier, when the episode initially starts, every queue value is 0. So now the concept of exploration and exploitation trade-off comes into play. We will use something called as Epsilon greedy strategy. In the beginning, the Epsilon rates will be high. The robot will explore the environment and randomly choose actions. The logic behind this is that the robot does not know anything about the environment. As the robot explores the environment, the epsilon rate decreases and the robot starts to exploit the environment. During the process of exploration, the robot progressively becomes more confident in estimating the queue values. For the robot example, there are 4 actions to choose from: up, down, left, and right. We are starting the training now. Our robot knows nothing about the environment. So the robot chooses a random action, say right. The pictorial depiction of the same is as shown in the slide herein. We can now update the queue values for being at the start and moving right using the Bellman equation. We now move over to steps 4 and 5, which is nothing but evaluation. Now we have taken an action and observed an outcome and reward. We need to update the function q of S and A, and the same is as shown in the slide herein. In the case of the robot game, the reiterate the score reward structure will be power will be equal to +1, mine will be -100, and end will be +100. The pictorial depiction of the same is as shown. We will repeat this again and again until the learning is stopped. In this way, the queue table will be updated. Let's now see the Python implementation of queue learning. The Python implementation of queue learning is as explained in the video which is shared herein.
If you want to learn how to train a reinforcement learning agent to play video games, so please stay tuned. In this video, we will discuss on a topic called queue learning, which will actually help us in training a reinforcement learning agent to play video games. I am Akshay and welcome to my channel. So before we start, in this video, we will cover what is queue learning, the mathematics behind queue learning, and a Python implementation for an RL agent in order to play a video game. So now let's begin. So queue learning is basically a value-based learning algorithm in reinforcement learning. But before digging deeper into technicalities, let's take a simplistic real-life example. Now, say there is a maze in which there is a robot at point A. There are mines at different locations. There is a power which basically improves the power of the robot, and there is an end location. The robot has to cross the maze and go from point A to the end location, that is the start point to the end location. So how do we train a particular robot in order to cross this maze? The reward structure of this particular game is as follows. If the robot moves one step, we basically penalize the robot in order to promote or encourage the robot in order to find the shortest path from the beginning location to the end location. If the robot touches the mines, it is minus 100 and the episode ends. If the robot touches the power, it is plus 1. And if the robot reaches the end location, then it is plus 100. This particular problem statement is ready for us. Now we need to train a particular agent in order to cross the maze. Now the question is, how do we train a particular agent? In order to solve that problem, we'll be using the Cue table. The Cue table looks like this, where the columns represent the action a reinforcement learning agent can follow, that is going up, down, right, left. And the rows represent the states, that is this number of states a particular game can have. In this case, there are 5 states. A Cue table is just a fancy name for a lookup table. The Cue table basically contains the value which has the maximum expected reward for taking a particular action. And the RL agent will always take the maximum value out of the Cue table in order to take any further actions. Now the question is, how does the Cue table gets initialized? Is there some oracle coming in and giving us the values for Cue tables, or is there some algorithm which we use in order to initialize the Cue table? Because in the initial stages, the Cue table will obviously be 0. That means when we start the game, the reinforcement learning agent knows nothing about the environment. So how do we basically initialize it, and how do we basically improve it? Because as we know it, and as previously discussed, this is an iterative process. So how do we do it? In this, here comes the role of the Cue learning algorithm. So the Cue function or the Cue algorithm basically takes 2 inputs, that is the state and the action. We use this particular formula in order to get the Cue values and update the Cue tables. But initially, all the values in the Cue table are set to 0. But as the RL agent goes on continuously exploring the environment using the Cue function, it gets better and better approximation by continuously updating the Cue values in the Cue table. Now let's understand this concept in detail. So before directly going into the updation part, let's understand the complete workflow of the Cue learning algorithm. This is the complete workflow of the Cue learning algorithm. Now starting up with the initialization of the table, in the initial state when the RL agent starts, all the Cue values are arranged and is set to 0. The columns are basically the actions, in this case there are 4, and the rows are basically the states, in this case there are 5 states. So this is how we initialize the Cue table before starting our exploration. Now talking of the step 2 and step 3, that is choosing an action and performing an action, these particular steps are basically done iteratively until unless the loop stops or we decide to stop the loop manually. The RL agent chooses a particular action at a particular state as per the maximum Cue value. But the question is, in the initial state when all the Cue values are 0, how does the RL agent decide which action to choose? Now comes the concept of exploration and exploitation trade-off. This concept of exploration and exploitation trade-off I have already explained in my previous video on reinforcement learning. So I would recommend, if you have an idea on this particular concept, it's very good, it's awesome. And if you don't have an idea, no worries, please have a look on this video and then come back and continue with this video. Now, coming back, exploration exploitation trade-off will be used in the initial states when all the Cue values are 0. This particular method or concept will basically allow the RL agent to decide which action to choose. We will use something called the Epsilon greedy strategy in order to solve this problem. The Epsilon greedy strategy says that there will be an epsilon term which will be set very high in the initial states when all the Cue values are 0, so that the RL agent explores the environment more and more, because we or the RL agent knows nothing about the environment. So the epsilon is kept very high so that the RL agent goes on exploring the environment. As the exploration goes on and the RL agent becomes familiar with the environment, slowly and steadily the epsilon rate decreases, There is a decay rate which we'll be placing in our programming example, which allows the epsilon to decay. Now, slowly, steadily, as the epsilon goes down, the exploitation starts. So here the concept of exploration and exploitation trade-off is fulfilled. Now, talking of our Maize example, we can see that the robot has to randomly choose an option. Say the robot chooses to move right. Now, after choosing right, the robot is at a new location, that is a new state. Now, the updation of the Q values will happen using the Bellman equation. Now let's discuss the step 4 and step 5, that is the evaluate function in the Q learning algorithm. So as of now, our robotic agent has taken a step. So the robotic agent is in a particular new state, that is S prime, and the robotic agent has got a reward, say R. Now we'll use the Bellman equation as shown to update the Q tables. So in this regard, in our robotic game, the reward structure looks like this, where if the robot gets the power, it is +1. If the robot is hit by the mines, it is -100 and the episode ends. And if the robot reaches the end location, then it is +100. So this is the reward structure which the robotic agent will be following while going through the maze. So to evaluate the Q value and update the Q table at this particular state, we will use this particular formula. So the new Q value at this particular state is equal to the current Q value plus some learning rate into the delta term. Now what's this delta term? Now this delta term is computed like this. Now after doing all the computational stuff, we see that our Q value has been updated to 0. Now it doesn't matter that this is updated to 0 because this is basically an iterative process. We continuously go on updating the Q value until unless the iteration stop or we basically plan to stop it manually. So hereby at the end we get a Q table which can be used to determine the best possible actions. So to recap, Q learning is basically a value-based reinforcement learning method in which we need to optimize and maximize the Q function. The Q table is basically used in order to decide which particular action our agent should take in order to maximize the reward. In the initial stages, the Q table is basically initialized to 0. So the RL agent has to take random actions and then iteratively the Q table gets updated. So to update the Q table, we basically use the Bellman equation and this is done iteratively. In the initial stages, as the Q values are already 0, so there is a trade-off of exploration and exploitation made. That means in the initial stages, the RL agent has to basically explore the environment in order to understand the environment. So it's very intuitive that the RL agent knows nothing about the environment, so it needs to explore in order to understand before it starts exploiting. Now let's see the Q learning implementation part.
So we are into the demo right now. So we'll start the coding part with the initialization of all the libraries. We are importing gem for the environment we'll be using. We are importing numpy, we are importing random, and after the libraries have been imported, we will first initialize the environment variable with the taxi version 2 because we will be using and we'll be solving the problem of picking up the customer and dropping it out at a particular location, that is a destination location, by a taxi. We'll be solving this particular problem using the Q learning algorithm. So after we have initialized the environment with the taxi version 2, we render the environment. We see that there is a taxi, this yellow color is the taxi, there are 4 locations and there are customers. Now we reset the environment, we re-render it and we check the action space and the state space. Now the action space is actually the number of actions an RL agent can perform. Now here our RL agent is the taxi and the state space is actually the number of states where this RL agent can come by taking some action. So we see that discrete action space is 6 and state space is 500. Then we encode all the states and we again see the states. There are basically 428 states. So we'll now start up with the Q learning algorithm. We will be first initializing the Q table with all zeros and the columns will be the action space and the rows will be the observation space. So we see that if we do Q table, we see there are zeros and there are the columns are the action space and the rows is the observation space, that is a state space. Then we initialize and set our hyperparameters and then we start up the training part. Now we have started with the training part. we see that the training is started and it's episode 100 and it's slowly and steadily increasing. We'll be basically training it for 1 lakh episodes and the output will be shown every 100 episode. So let's wait for the training to be complete and then we'll see what the output comes in. So the training is complete. Now we can see that our Q table has been initialized by some other value. Now for example, as already discussed, that the RL agent when at a particular state will take a particular action with the highest Q value. Now according to this, the highest Q value is 63. So this particular Q value will be taken by the RL agent when the RL agent is at 428 state. Now we can start the testing part. Now when we do the testing part, we see that the results are awesome. We see that the average penalty per episode is 0 and the average time spent per episode is 12.35 and it's only tested for 100 episode. Now we see that by implementing Q learning algorithm in Python in a small state space like Taxi version 2, it's very efficient to solve this particular problem.
So we have seen how Q learning can give fantastic results in a small state space. But now the question is, in the real life, the state space is not small. There are millions and millions of states in a particular real life scenario. For this, Q learning is basically inefficient and is not suggestible. So in my next video, I'll be taking into consideration some more strategies which we can use in order to provide the RL agent to find best possible actions using some of the other algorithm. In our next video, we'll be discussing about the deep Q learning. So thanks for watching. And